Hi, welcome to another episode of FiveSpire. My name is Pia. In today's video, we're going to be going over the Linux file system. The topics we're going to cover are the file system layout, navigating the file system, and we're going to get a bit more technical with inodes and character devices. By the end of this video, you're going to have a better understanding of the technical details behind the file system and what makes it so unique, especially if you're coming from a Windows background. So let's begin. We should start off with the definition of a file system. Quite simply, it's just the hierarchical structure of files and directories. In Linux, it resembles an inverted tree with the root directory up top, represented by a slash, and from there it branches out. Each branch can either point to a file or directory, with directories subsequently pointing to other files and directories. And with this structure, we can see why it's called an inverted tree. Navigating this file tree is quite simple once you understand its structure. When we launch a terminal, we're placed in our home directory. You can tell that with the tilde character in the command prompt. The tilde in bash is just a shortcut for the user's home directory. But if you're ever unsure where you are in the file system tree, just run pwd. It's the present working directory command. We list what's in the current directory with the ls command, the list command. Right now my terminal supports color, so I can tell which files are directories and which are just plain files. However, if you don't have terminal that supports colors, run the ls command with the -l flag, and you can tell the directories by the D character in the first column. We can change our working directory to the documents folder just by typing in cd documents. You can see my command prompt has updated accordingly to reflect the new working directory, but if we're unsure, we'll just run the pwd command once again. Now, if we run the ls command, it'll print out what's currently in my documents folder. To go up one level in the tree, it's just cd ... That's all there is really to navigate the file system, but however, you should know the difference between absolute and relative path. If you remember before, we changed directories by typing in cd documents. That works because documents is a subdirectory of my home directory. We could also have wasted some keystrokes by using the absolute path, meaning the address starting with the root directory. A few more things you should know is going up multiple levels, you need to include the / as a delimiter between levels. So moving up 2 levels requires cd ... And now we end up in the home directory. Not my actual home directory, but the /home folder that holds all the user files. You have to remember that Linux is a multi-user OS, meaning more than one user at a time can be logged into the system. This particular system has 3 users, Dev, Fred, and myself, PD. Trying to change to the Fred directory will give us an error because we don't have permissions to view Fred stuff. I'm not going to go into too much details about file permissions in this video, but just know that files and directories have permissions attached to them for things like opening and modifying, and unless you have access rights to them, you'll be denied. So to get access to Fred's stuff, we actually have to switch to his account using the su command, the switch user command. And you can see that when we logged in as Fred, we were automatically sent to his home directory. And from here, we can list his contents. And it looks like Fred has his own documents folder, so we can check that out. And nice, he has a subscribe to FiveSpire text file. Just to demonstrate, let's try changing directories into my old documents folder as Fred. And yeah, permission denied. We're not going to be able to see that unless we switch back to my account. To understand how Linux works, we need to look at the direct subdirectories of root. These subdirectories are more or less standard for all Unix-based systems, including Linux. There are man pages that you can reference with man7 higher. These pages document folder names and what they contain. There's several dozen of them listed here that you're free to read on your own, but in this video I'm just going to go through the more important ones. The bin folder is supposed to contain the minimum executables that are required to bring up the system or repair it, but these days it pretty much holds every command. Boot folder contains the bootloader and the kernel. You should never manually modify or delete any of these files. Instead, use tools like your distro's package manager to install or remove kernels, and Grubby if you're using Grub2 as your bootloader. The etc folder, at least I've always called it the etc folder, but I've also heard people just call it etc. This is the folder that you'll most likely be in a lot, as it contains the majority of your configuration files for the system. I'll show you a demo by manually editing a configuration file. I'll just disable the main repo. Fedora's repo configuration files are located in the yum.repos.d folder. Each one of these repo files are configuration files for a single repo. I can use the DNF program, which is the package manager command line program, to check which repos are active by typing in DNF repo list. And you can see that the Fedora repo is active. Now, if I wanted to manually disable the main repo, I can open up the fedora.repo file in a text editor, in this case using Vim. Now, you have to remember that files in the etc directory are system files, so I need to open them up using the sudo command so I can edit them with root permissions. With the file open, I see there is an enable variable and it's set to 1 for true. So disable is just as simple as changing the value to 0 and then saving and quitting Vim. Now if I run the repo list command once more, I show that the Fedora repo is now disabled or is not active. Many commands will have an option of setting common configuration fields directly. Sometimes you either forget the syntax or just find it easier to manually edit the configuration file. It's really up to you. But let's go ahead and re-enable the repo using the command program. And it's to re-enable the Fedora directly through the command line program. It's DNF config manager, and we set enabled and we pass the Fedora name. And we can rerun the repo list command once again, and we can see that Fedora is back in our list. And let's just, for the hell of it, let's just take a look at the repo config file, and yep, enabled is set back to true. Okay, continuing with our quick tour of the root subdirectory, we have the lib folder next. It contains all the shared libraries. Lib is similar to the bin directory, where its role was to contain the minimum libraries to boot up or repair a system, but now it pretty much contains all the shared libraries. The home folder you saw earlier in the video, it contains the user files. Temp folder will contain files that can be deleted at any time. Most systems will clear this folder upon boot, so don't put anything important in here. The user directory once contained the user files that are now stored in home, which is why we still awkwardly call it user. Today's its main role is storing all the installed share programs, their source files, and program documentation, including the man pages that we referenced. And finally, last is the var directory, which stands for variable, and the variable directory contains files that tend to grow or shrink in size. This is where emails were once stored before everyone started using web-based emails. Database files are still stored here, and sometimes you'll see admins putting their web servers and FTP servers in this directory. So you may be asking yourself, why this particular home directory hierarchy? Something that seems very arbitrary, like why move users files away from the user directory to a new folder called home. Even emails seem to make more sense if you stored it directly in a user's home directory instead of a weird sounding variable directory. To understand why, we have to understand that the Linux file tree is displayed as a single logical volume, all starting from the root. Unlike Windows, there's no concept of drive letters like Windows users would be familiar that C is for the main drive, A is for floppy, and Z may be mapped to a network drive. Linux instead mounts these devices to the directory path. Knowing this fact and remembering that Unix was built in the 70s during the mainframe era, where servers were the size of refrigerators and workstations had less power than remote control, this may clue you in why this directory structure starts to make more sense. Like we had the bin and lib folders had to be stored locally and they had to be as small as possible. Temp was mounted to a fast drive. User was mounted to a large read-only network drive where they could store the shared programs and users can query documentation. And var was a read-write network drive that stored users' messages and print jobs. In today's world of powerful PCs and virtualization, this type of hierarchy makes less sense. In fact, majority of Linux distros will only have 3 to 4 partitions by default. They're mounted on root. The home directory would be a different partition. Boot would be another one, and then you would have a special swap partition. Okay, now that we have all the history cleared, let's take a look at the concept of single logical volume in action by mounting a partition to an arbitrary path in the file tree. Run the lsblock command and get a listing of devices, their size, and their mount points. I can see I currently have 3 different devices. SDA, which is a SATA hard drive, split into 3 different partitions, and those are all mounted. I have another SATA drive, an SDB, and that just contains a single partition, which is yet to be mounted. And for the keys, SRO is just my CD drive. So let's use our unmounted partition on SDB to act as a backup. First, we need to select a mount point. I think I'll use a backup directory in my home folder. But first I have to create the backup directory. So make directory backup. Now I can go ahead and mount the device using the mount command. And with mount, it's a system related task, so I have to sudo first. The mount command syntax is just mount the device path. In this case it is dev/sdb1 and the mount point. The T flag specifies the file system format. In this instance it's XFS, which is the default file system for Red Hat distros. Okay, we didn't get an error message or anything, so everything looks working. We can just go ahead and check. Yeah, if you notice that now the backup directory is owned by root. This is because we mounted the drive as root. So to change that, it's just a matter of changing the ownership back to the PD account. Doing that will allow me to read and write to the device. So we can just use the change ownership command, and yeah, let's not forget the recursive flag. Okay, now that I own the drive, we can go play with it. And as you can see, the partition was completely empty. Just add some new files, a touch new file text, a hello world text, and why not please subscribe text. And we can list the directory content, and they're all there. And these files are stored in the SDB1 partition. And if I continue down, modifying anything in this backup tree, it will be stored in the SDB1. So if I didn't know anything about this partition, it would just look to me like it's on a single logical volume. So we can just unmount the drive by using the unmount command. And now if we look up the backup directory, it's completely empty because it's now, the partition has been unmapped and unmounted from the backup directory, and then the files that we created are still stored on the partition, but we can't view them because it's not pointing to the partition anymore. But just to show you that mount points are arbitrary, let's quickly remount the partition, but this time to a different directory. We make a new directory, backup-new-mount, and we can remount the command again. We gotta make sure to properly type it, and we'll execute. And now we have the SDB1 partition pointing to this new directory, and all our old files should be there that we created before, and we can check just now. Perfect. Linux doesn't have many naming restrictions. There are 2 illegal characters, the null character, which is Unicode 0000, and the /. because the / is used as a delimiter in paths. Linux does have a 255 byte size limit to file names. How many bytes a character takes depends on your computer's encoding, but majority of computers today are using UTF-8. You can check that by running echo $lang in all caps. UTF-8 uses variable encoding, so characters found in the ASCII table, which are numerals in uppercase A to lowercase z, take 1 byte. Extended ASCII that includes Cyrillic and Latin characters like umlauts and accents take 2 bytes, and the rest of the characters in the UTF table, including things like other foreign languages and musical notation, take 3. This all means if you had a file name consisting of only kanji characters, you'd have a limit of 255 divided by 3. It's something like 86, I believe. So let me show you. We can try creating a character of just the heart character, which is Unicode .2764. This character is 3 bytes wide. We'll cut it and then paste it a bunch of times. Nope, file name's too long. For curiosity's sake, let's just see how long that file name was. We can use the word count command to tell us, and we have to use the M flag to count each character. Yep, 107, which is obviously way too large. The other thing I wanted to point out is that Linux doesn't care at all about file extensions. In our last command, we created we tried to create a text file. The text file extension is just for us humans. Linux itself uses several what they call magical tests to determine the real file type, and none of which is actually looking at the file extension. To show this, here I have a ping file, or something with a file with a ping extension. I can make sure it's a ping file by using the file command. Yes, it checks out. File is also nice enough to give me a bit more information about the particular image, including the size and the color profile. We can try changing the file extension to a GIF file to see if we can fool Linux. Right here I'm using a fancy way to use the move command using the bash expansion. Okay, extension hasn't changed. We can rerun the file command, and nope, it's still showing that it's a ping file. And quickly, to really prove my point, I will rename it a text file. And yeah, still PNG. Okay, now let's move on to hidden files. With Linux, hidden files share no connotation with secret. Hidden files are just a way to declutter the directory listing and not to keep your file secret or locked away from other prying eyes. You can easily view hidden files just by using the -a flag of the list command. Only special thing about hidden files is they start with a dot. So to create your own, just create or rename a file for dot at the beginning. LL we can check, and nope, gone. LL-A, and yep, it's there. Links are conceptually fairly easy to understand, even if they break our tree model for the file system somewhat. We can just think of them as shortcuts to another branch. It's simple enough, right? Well, that is until they're not. Let me show you. In this scenario, I have 2 different to-do files, one in my home directory and one in my documents directory. Quite silly to maintain 2 different to-do lists, but I'd also like to keep my to-do list as visible as possible. So we can do that by creating a link. First, let's figure out which to-do file to keep. Seems that the to-do in my home directory is the old one, and I should keep the one in the documents, but let's just verify, and yep, this looks like the most up-to-date to-do list. Like the video, subscribe to FileSpire, and so on. Okay, now that we figured out which to-do to keep, we can just delete the old one and create a link to the one in documents. We do that by using the link command, the ln. In Linux, we can create 2 types of links, a hard and symbolic version. I'll create both versions to easily show you the difference between the two. ln takes a target first and then the link name. On the surface, they don't act very much differently. Reading from these 3 different files all output the same content. I can add a new to-do item by appending to any of the files. In this instance, I'll add the following. Follow your host on Twitter at Pia, and I can append that to the end of the documents to do. We use the 2 angled brackets, and when we do that, it just appends. A single bracket would overwrite the file, which obviously we don't want to do. Okay, now we can check the contents of the link files. They contain the new appended to-do item. Okay, well, that was all easy enough. Most people actually don't start running into issues with links until they start deleting or moving around links or their target files. And when this happens, you can tell the difference between the 2 different types of links. If I rename the documents to do text to documents to do old, I'll still be able to access it through the hard link. However, the soft link is completely broken. If I list my contents, I can actually see that my to-do soft link is red, meaning that the link is broken. I can fix this broken link by creating a new to-do file. And if I check again, my soft link that was red is now a soft blue, meaning it's pointing to a valid file. And if I print out the contents of the soft, it'll print out the new to-do file, which is right now a single line header. However, if I check the context of the hard link, it still prints out the original to-do. To figure out what is happening, we have to learn all about inodes. A file object in Linux only contains 2 properties, its file name and an inode number. It is this inode object that contains everything else that is needed to access the actual bytes off the hard drive. This includes a hard drive sector address, but also other metadata including dates, file ownership, and file size. We can view a file's inode information by using the command stat. We run stat with the hard link and the old to do, and you can see that it's actually the same inode, number 127.134.02. This is why when I moved the to-do file, I was still able to access the contents off the hard drive. Even if I deleted one of the hard link or the original file, the contents would still be there because the inode would see that there's still a file referencing it, so it'll tell the Linux kernel that no, the section of hard drive that it uses is not free. So that's a hard link. A soft link is quite different. Instead of pointing to a specific inode, a soft link creates its own inode file, and that inode references a path. So if you remove what's at the end of the path, you essentially break the link. You can fix this by just moving back the original file to the old path, or just creating a new file. Okay, then the question is now, which one should I use? Well, that's easy. Just remember always to use a symbolic link. Or I should say, you should never create a hard link manually. Hard links have one major drawback, and that is you cannot create a hard link between different devices. You can run the df command with the I flag to see what I mean. The partitions dev sda1 and dev sda3 have different inodes available and used, as each partition has its own inode index. So inode, let's say number 124.5851 will not be the same inode on another partition. Hard links really only have their use in backups. With the way inodes behave, it allows you to create a snapshot without taking up too much hard drive space. Actually, this is how Apple's Time Machine works. So it would create an initial snapshot of the hard drive, and then I believe every hour any modified files would be stored, but the rest would be untouched, only creating hard links of the old files, and hard links don't take up any space, so you can create hourly backups without eating up all your hard drive space. The saying everything is a file is an important concept to grasp, and it is one of the ideas that make Unix truly unique. Although I think the concept is easier to understand if we say everything is a byte stream. If you think of a plain text file as just being a sequence of bytes, then you can extend that concept to other devices, like say maybe a printer can be a file that just prints out whatever you send to it. This very concept in Unix allows us to do some wild things. meaning we can mount special device files as long as they satisfy certain methods. Things like reading a file with cat or writing to a file using a pipeline redirection. The proc subdirectory is actually one of these special file systems. It allows us to read kernel and CPU runtime information. If you notice here, I was able to cat the proc uptime file, and what that does is just prints the uptime of my computer system. Running again will obviously give me updated figures. Actually, many programs are just thin wrappers to these special devices. They read the outputs and then usually prettify them for human consumption. Like, these uptime figures don't mean much to me, but if I run the uptime command, I get a more readable output, and using the P flag for prettify, I even get a more understandable one. Another example is the modules, cat modules, to see what kernel modules are loaded. And there's a command for that, and that's just lsmod. Those files are read-only, but there are other special files that we can send output to. Let's send a message to ourselves through the terminal's device file. We can find out which terminal we're using by running the tty command, and this gives us the path to that special device file for our particular terminal. So it's dev pts0, and knowing that, we can send ourselves a message using the echo command. So we'll just send ourselves a echo hello world, I hope you're enjoying this video. And there we sent ourselves the message. And just to show you that it actually works, we can redirect the old echo command to a special device file called dev null, and that's just like a black hole over system. Anything we send there just gets tossed away. Dev null is useful for when you run a command that you don't want to be bothered by the printout, so you just redirect all the output. Wow, that was a lot to cover. Went from the basics of describing the Linux file system as an inverted tree, and you learned how to navigate it. Then we looked at the root subdirectory and a bit of history of why they're structured that way. We mounted a partition to demonstrate the concept of the single logical volume. Learned that the maximum file name size is 255 bytes. And after all that, the difference between a hard and symbolic link and which one you should use. And then we touched on the concept of everything as a file. I do hope you enjoyed watching this video and now have a better understanding of the Linux file system. My only request is that if you indeed enjoyed watching the video, is to share it with your friends and colleagues. Maybe they'll find it as informative as you did. As always, let me know what you think. You can post a comment or send me a tweet, and don't forget to like and subscribe to the channel. Thank you.